This is a review from last time. We started talking about the work energy theorem. And what the work energy theorem says is that when an external force does work on a system, something about the system changes. What we call that is that we call that a change in energy. By definition, we see here that the work done by an external force, a constant force, is the external force times the displacement, and that's the change in energy. And the key thing about this work energy theorem, it's a way of looking at systems. And I think that's really important right there. So when we look at a system, we want to think about positive, negative, and zero work. So remember, it's a way of thinking. Positive work occurs when the external force and the displacement point in the same direction. So if I have an external force and I have a displacement vector pointing in the same direction, then we call that positive work. In other words, W is greater than 0. So when I look at my system, which is this violet, then the work coming in, the work is a transitional thing. So the work transitions the energy, and that work is converted into stored work, which is what we call the change in energy. So now, in this case, I'm going from a lower energy system to a higher energy system because there was a so-called flow of energy into the system. So if I look at my bar diagram, I start off with some initial energy E1. Now I do external work on this system. In other words, that work is flowing into the system as stored work. So my system already started at E1, and you could see how I put those dashed lines to signify E1. So then that light blue is what went from external work to the change in energy of the system. It's this stored work that has meaning, not E1, not E2, but this change in energy. So positive work has increased the energy of the system, and we have a tendency to say that there's a flow of energy into the system, and therefore it increases the energy of the system. Now, if I go to negative work, that occurs when the external force and the displacement point in opposite directions. So here you could see that the displacement and the external force are in different directions. They're different by 180 degrees. This negative work means that the work is now negative. Again, work is a transitional thing. So what is the transitional thing? I imagine that when I do work, I am taking energy out of the system, but the work is what's doing that. And so what happens here is that when the system changes, I'm now going from a high to a low energy state. So because the work is negative, you could see that I have a larger E1, and then the work is negative. And as a consequence, you could see that there's a reduction in the energy of the system, which I should have called that 2 instead of 1. So this work causes a negative change in the energy. That's how I go from a high to a low. Now, once again, negative work decreased the available energy of the system. There's a flow of energy out of the system. And the one that believe it or not, that's probably the most important to conservation of energy is zero work. But what you find here is that there are two possibilities. One, zero work is done if the external force and the displacement are perpendicular to each other. So you can clearly see that there's a right angle between the force and the displacement. That means zero work. So why is that zero work? Because in order to do work, there has to be a displacement. This force does not cause a displacement in the vertical direction. Therefore, it can't be work. So perpendicular forces never change the energy of the system because there's no displacement. And in this case, there's no displacement in the vertical direction. But it's the second situation that's most important to energy. If the exact same flow of energy goes into and out of the system, then no work is done. Well, I start off with the system, and if I end with the exact same system, then that means that the energy of the system did not change. Over here, I looked at a change in energy because it went from violet to orange. Of course, this is just this, a picture viewpoint of how the system has changed. Here, I'm explicitly trying to show that the system did not change. So if the energy of the system did not change, then it means here that the energy coming in versus the energy coming out are equal and opposite. In other words, I didn't write this clean enough, so let me rewrite this again. In other words, the work that went in versus the work that went out are equal and opposite, and therefore they cancel each other out. That's what we mean by the work energy theorem. And it's a very, very powerful way of looking at these things. So I believe I only have two more things. So I don't remember what my numbering system was from before. Let me go back and look online to see what my numbering system was. Sorry for the delay. I didn't think about that. That way we have consistency on how I look at my numbering. So we went up, it looks to 4. So now I want to go in and I want to look at 5. So this is our 5th thing that we've talked about to try to interpret this. So now what I've been doing here is I've been showing you pictures of a system. Now, maybe I don't want to do this. Maybe I don't want to do this. What I want to do here is that now let's look at an example. And here, what we're going to show here is that we're going to have a system which is going to be a block. So now let's go and look at this thing here. So what am I seeing here? Suppose that what I'm going to do here is that I'm going to drag a block across a surface with friction. And what I want to do here is that I want to look at what does work and what does not do work. What increases the energy of the system? What doesn't include the energy of the system? So for the sake of simplicity, let's say that we're going to deal with dynamic equilibrium here. So if we're dealing with dynamic equilibrium, I have a block. So what's my block going to look like here? So I imagine that I have my block. And my block is this yellow block. And what I'm going to do is that I'm going to apply a force on this block. And I'm going to pull it in this direction. In other words, my displacement is in this direction. And this is my surface here. So when I go and I look at this thing, what we go in and we show here is we say the following thing. This is my system. Now, if this is my system, what are the external forces act on the block? And the way we answer this is that we draw a free body diagram. So if I draw a free body diagram, then I imagine here that I'm going to go for the center of mass. And now I start to look at my forces here. So here's my force right here, which then means I'm going to have a component that points in the x direction. I have a component that points in the y direction. Now I have a normal force. So then I'm going to say that I have a normal force that's pointing up, and I have my force of gravity. So since this thing is sliding across the surface here, and it's in dynamic equilibrium, we know that the normal plus the force in the y direction has to equal to mg. Now I have one more force. So if this guy is, if f of x is that size, then this must be the frictional force going to the left. Now, I know my displacement is going this direction, and I know I have a velocity. You know what? Let me move this a little bit. And I know that I have a velocity going in that direction with 0 acceleration. So when you look at this thing, if we count the forces here, the forces external to the block, you can clearly see that we have f of x, f of y, the normal, mg, and f of k. In other words, there are 5 different workings that are going on. So from this counting, we could then come and say that since there are 5 different external forces, there are 5 workings. So then I start to look at this thing. So the first thing that I'm going to say, 1, which does positive work? So when I look at the block, what I'm seeing here is that there's only one force that does positive work. And what I'm seeing here is that I'm looking at this and I'm going, okay, here's my system. So now I find that the work of f of x is positive since f of x and the displacement are parallel. Therefore, the work of f of x increases the energy of the block. Then I go to the next one here. And then I go, what about are there any negative works? And so again, if I look at the block here, we can see here is that in this situation, there is a negative work, because when I go and I look at the energy, I look at the work, what I'm seeing here in this situation here is that I'm seeing that there is work done by friction. And that work done by friction is negative, since I see that my frictional force is going that way, but my displacement is like this. So therefore, the work of friction decreases the energy. And then finally, we can ask the question, is there anything that does zero work right away? In other words, what forces are perpendicular? And so when I look at my block, and we say, what is outside of this block? We can see that there are three forces. There's the normal, there's F of Y, and there's mg. So what we're seeing here is that in this case, we can see here that mg is coming down, but that's perpendicular to the displacement. And then I have my normal, and I have my F of Y, and these guys are perpendicular to here. So that again implies that since these forces are perpendicular, right? So if I look at this force, or if I look at that force, and that's the displacement, this implies here that the work of the normal, the work of F of Y, the work of gravity is equal to zero. And do not change the energy of the block. So just pulling these guys apart, we look at that. So now, what do we know? We have a block. So then I look at the net work then. The work energy theorem then says this: I have a block. And as it moves across the surface, what do I see here? If this block has a displacement in this direction, and if this block has zero acceleration, then one of the things that we can say here is that the net work in this situation tells me it should be the net force times my displacement. But according to a free body diagram, then if I pick this to be my positive direction and this to be my negative direction, then this net force says that I have force in the x direction minus the force in the negative x directions times this displacement. That net force is zero, and it looks, and therefore this implies that there is no change in energy. So using Newton's second law, we can write this and just say, yeah, we knew that the net force was already equal to zero because there was zero acceleration. But that's not the way we view things in the language of energy. In the language of energy, we don't look at it this way. So in the language of energy, we then say that we have a block. And as we have a block, and I look at my system, what actually happens? What happens here is that there is a flow of energy flowing into the system due to the work of f of x. And by the way, I've now changed my colors, so let me go back and not do that. That's how I defined f of x. So this is flowing into the system at this rate. And then what happens here? There's a flow of energy that's coming out. And as it comes out, there is work, negative work, done by the force of friction. So as a consequence, then what we see here is that this block if it is now moving at some velocity with zero acceleration, this block will continue to move with zero acceleration afterwards. In other words, when I look at this as a bar diagram, I have a system. What is my system? It has this amount of energy. Okay, let's say it has this amount of initial energy. So if it has this amount of energy, I see that there is positive work done by the work of f of x. But simultaneously, there is negative work done by the force of friction. And so remember, everything above, so if this is my zero line, then everything above this is positive, everything below this is negative. So you can see here is that these two guys are doing what? They are offsetting each other. The flow coming in is exactly the same as the flow coming out. And so then afterwards, the energy of the system is exactly the same as afterwards. That's what the work energy theorem tells you if it's in dynamic equilibrium. But what if I have a non-equilibrium situation? So if you come back up here, then we're still looking at this system here. Right? I still have all of the same types of things here. So if I'm looking at this guy, what do I see here? Then I have the following thing. So from the free body diagram, now I have a block that's doing what? I have a block where there I have a system, and let's just say for the sake of argument, that this block is speeding up. So if it's speeding up, now I got to look at my system here. So then the free body diagram then tells me the following thing. I still have my same forces. I have my force in the y direction. I have a longer f of x. I still have a normal going up, and I still have mg coming down. So the big difference is that when you look at that, you can see here that I have unbalanced forces. That implies that I have a net force that's then going to be f of x minus f of k. This will be a positive net force. So in other words, I have a net force, which we already knew that, and I have a displacement. So what is the language of work here then, or energy? What does the language of work and energy mean? So in this situation, the work energy theorem tells us the following thing. I have a block. And when I look at my block, what do I see in my system? What I see here is that the amount of energy flowing in is much higher now, compared to the amount of energy taken out of the system. So now what happens here is that afterwards, I am going from a low energy state to a high energy state. And as a consequence, the system has changed. What do I mean that the system has changed? Well, this block is now in a different energy state, right? It's going to be in a different energy state. And because it's at a different energy state here, the way I draw this in a bar diagram is that I go like this. I have this amount of energy coming in. Excuse me. This is my original energy of the system. And then what happens? I do work. I do more positive work. And in this situation, you're seeing here that according to what we drew before, the only difference here is that there's more work done by f of x than friction. And as a consequence, what this really shows me here is that I still have energy 1, but now I have a network that's been done here. And this network is a positive network. And then by conservation, by the work energy theorem, the overall energy of the system has now increased to E2. So when I'm looking at this thing, what I'm really calculating right here is this change in energy. Therefore, the work energy theorem then says that I have a change in energy. In other words, I started at my energy 1 state. I did this amount of net work, and as a consequence, I went from a low energy state to a high energy state. That's what I mean by the work energy theorem. Picture-wise, that's what you're seeing here. So what's important about this here is, in summary, if the network is equal to 0, in this case, that means the system is in dynamic equilibrium. However, if the network is not equal to 0, and therefore the change in energy, then the system is in non-equilibrium. In other words, this tells us about constant velocity, and this tells us about acceleration. We don't need Newton's laws to tell us when a system is in dynamic equilibrium or it's in non-equilibrium. We just look at what's happening to the work. Did the work change the system? Then it's in non-equilibrium. If the work didn't change the system, then it stays in dynamic equilibrium.